Hello and welcome to the Introduction to Optimization exercise class 6. In this class we will learn about formulating integer optimization problems and optimization problems with binary and integer variables. In the first demo we are given the following verbal description and we will formulate a linear optimization problem with integer and binary variables and then solve it with the Julia programming language. This problem has three parts. In the part A, a retailer buys a product from a factory and sells one piece with €2 profit. The retailer has to pay €1,000 to the factory to be able to buy the product, and the maximum amount of products the factory is able to produce is 750. And the question is, how many products should the retailer buy, if any? In the part B we ask a following question to the part A, which goes as, how about if the retailer has to pay the €1,000 only if the quantity of purchased products exceeds 200 pieces? Finally, in the part C we have to formulate a new optimization problem, which is described as follows. A farmer has 15 boxes of apples and two fruit retailers, Apeli and Topeli, who want to buy his apples. For one box of apples, Apeli is willing to pay €25 and Topeli is willing to pay €32. If the farmer sells more apples to Apeli than Topeli, Apeli will pay the farmer 450 extra. Similarly, if Topeli gets more apples than Apeli, he will pay the farmer €270 extra. And the question is, how many boxes should the farmer sell to Apeli and Topeli to maximize his profits? Let's look at the solution to part A. In part A we have decision variables, which are the quantity of purchased products denoted by X, and they are integers, as we see here. And the decision to pay the fee to the factory is denoted by the variable Y, where it's 1 if the fee is paid and it gets value 0 if the fee is not paid. And then the retailer wants to maximize his profit, so he subtracts the expenses from his income, which is this. And because the retailer can only buy 750 products if he has paid the fee, meaning that Y is equal to 1, and 0 products if he has not, which indicates that the Y is 0, we get this constraint. Now below here we have the solution to this problem, which is that the retailer should pay the fee to the factory and buy all the 750 products to retrieve a €500 of profit. And we can go to Julia and verify that this solution is correct. Let's import the jump and CBC and let's run the model. And as we can see, the optimal solution is the 750 products that he should buy, and the indicator variable Y is equal to 1 and the objective value is 500. In part B we have to change the constraint, this one, such that the retailer is able to buy 200 products without paying the fee, and the resulting constraint will be this one, and we will change this constraint into this one. Now the optimal solution is still the same as part A, and we can verify this using the Julia and creating the model. Here we create the model as in part A, but we change the constraint to this one, and then let's optimize it. And as we can see, the solution is still the same. Finally, let's look at the solution to part C. In part C we have decision variables, which are the quantities of the boxes sold to Apeli, denoted by X1, and to Topeli, denoted by X2, which are this one. And the binary variable Y, which indicates who has more apples. And 1 indicates that Apeli has more apples and 0 indicates that Topeli has more apples. And the objective is for the farmer to maximize his profit from the boxes and the extra, which is formulated here. And because the farmer can only sell 15 boxes in total, we have this constraint where the total amount of boxes is below 15. And if the boxes sold to Aapeli is higher than to Toopeli, then the indicator variable y has to be 1, which is forced by this constraint where the m is a large number. And also if the x1 is less or equal to x2, then the y has to be 0, indicated by this constraint. Now let's look at the solution, where the optimum is for the farmer to sell 8 boxes to Aapeli and 7 boxes to Toopeli, and he receives the extra pay from Aapeli, and his total profits are equal to 874 euros. Let's verify it in Julia. And here's the full model. Let's create it. Let's optimize it, and let's look at the optimized values. And as we can see that they are the same as described in the solution. However, we should note that if the model would have a feasible solution where x1 would equals x2, it would pick it as the most profitable option. However, this condition where x1 plus x2 is less or equal to 15 prevents that condition from happening because x1 and x2 are integer variables.